The other video was getting too long, so now this is part 2. These last 3 examples, 6, 7, and then problem 65 from the textbook. So example 6, the way this works is that we're going to use GAPC up until this point. This is all conservation of energy, right? So this, I have gravitational potential energy, I have elastic potential energy to start with. I don't have any kinetic energy, right? It's being released from rest. It's just released, which means you're just letting it go. And then I've got this non-conservative force. So the energy, I'm figuring out what the velocity is here at this point. So I'm setting my datum here. Right. So at this point, all it has is kinetic energy. So I can solve for the velocity here, and from that use projectile motion kinematics to figure out how far this goes that way. All right. So let's take a look at our GAPC equation. This is compressed, so I've got 1/2 kx squared plus mgh1. That's it. That's all the energy I have at the beginning. And then the work done by a non-conservative force is mu mgl, so L, L1, just L, equals 1/2 mv squared. And v is the velocity at that point. That's it. I don't have this in terms of any numbers, so all I'm going to do here is solve for v here. So v is going to be, let's see, can I simplify anything else? I can multiply by 2. That's about it. So this equals, do I divide by m? Well, if I divide by m, then this goes away, and I just get this over m. So v is going to be the square root of this. So the square root of kx squared over m plus 2 mgh1 minus 2 mu gl. That's the horizontal velocity at this point. Now I want to find out how long is it going to take for this to reach the bottom here. So y equals 1/2 gt squared, but y here is actually h2. So this is h2. So t is the square root of 2h2 over g. That's the time it's going to take to fall. The distance it goes then is going to be this speed times this time, because this is the horizontal speed. That horizontal speed times the time it takes to get down is going to give me the distance that it goes. And so this is then going to look like, so I'm multiplying this into here. So the distance, do we have some s? It's going to be the square root of, so then 2 times this is going to be 2 h2 kx squared over mg plus, now this is going to be 4, oh, sorry, this m shouldn't be in here, getting rid of that. 4 g's cancel out, so I just have h1 times h2, and then minus 2 times 2, so it's 4. Mu, g's cancel out, LH2. Let me check. How does that look? Yep, it's nasty, but just leave your answer like that. That's the answer. Okay. Let's take a look at example 7. I'm just going to talk through this one. The idea here, the block travels with initial velocity, so we've got numbers. So it has an initial velocity, but we need to pay attention to the heights here because we ask ourselves at the beginning, what type of energy does it have? So initially it's got kinetic energy. All right. Does it have any potential energy? Well, if we look at the heights, we see that the first hill is 4 meters up, but the last hill is 6 meters down. So I'm going to use that bottom height as my datum. That means we're starting off at a height of 2 meters. So plus mgh. Okay. Now I'm going to look at the work done by all these other forces involved. So first of all, I have friction going up the hill. So what is that friction going to look like? The hill's like this. The block is going up. What is the force of friction on this? The force of friction is going to be mg mu mg cosine theta. Right. Mg cosine theta is the normal force. This is, and this is what mu is. So then the work done by this force is mu mg cosine theta times just that distance d. So I'm going to call that d1. So minus mu mg cosine theta times d1. Okay. Then I have a 12 Newton force being exerted on it in a wind tunnel. So that's a positive force. It's being, right, it shows you the distance or the direction that's going. So plus, let me just call that FA. It's an applied force times D2. And then, what else do I have? Then some more friction. So this one is just mu mg. So this will be minus mu mg d3. And then going down that other incline, I already took into account the potential energy, right? All we care about for the gravitational potential energy is the beginning and ending points. So this last one is going to be minus mu mg cosine theta d4. That's it. Equals 1/2 kx squared. At the end, it hits this spring, and it'll be compressed some distance. That's all we're asking for. So we're taking our ending point when it's at maximum compression. All right. So that's really it. All the physics is done. At this point, the only thing that needs to be done is you plug in all of the numbers and you solve for x. I'm not going to go through that and waste time on the video, but if you go through, you should end up with x equals 5.3 meters. Okay, and so even something like this, where there are all these different things, you've got, kinetic energy, you've got gravitational potential energy, you've got 3 different places where there's friction, there's a wind tunnel, and then a spring at the end. All of that can just be put into one big equation, right? Your initial energy conditions, all the things that are adding to or taking away from the energy in the system, and then whatever the final total energy is at the end, and you solve. Okay, that's it. All right, this last example from page 195 in the textbook. This one can get a little bit tricky. So let's take a look at what we're doing here. We've got the elevator falling down, and it's going to hit some spring. This is 1,800 kilograms. Let's just write down the things that we know. This distance, so it's 3.7 meters above the spring, above the top of the spring. That's important to know. And the spring has a constant, K, of 0.15 meganewtons per meter. And then the safety device clamps on the cab so that there's a constant force of 4.4 kilonewtons opposing the cab's motion. So the idea is that, right, those clamps click onto these poles. So what I now have is a friction force of 4.4 kilonewtons, whether it's moving down or up, because we're going to have some bouncing going on. And so the first thing we want to know, find the speed of the cab just before it hits the spring. So it's falling some distance, this distance, 3.7 meters. Right. So initially, I'm going to set, just for part A, I'm going to set this as my datum. All right, and I can change this as I go to the different parts. I just have to stay consistent. So I'm going to set this as my datum. I have mgh. I've got gravitational potential energy. Now I don't want to go right to the end yet because there's some work being done by friction. So mgh minus this force of friction, but the force is given over some distance, right? What's the distance it goes? Well, it goes the same distance, h. so minus the force of friction times the height, equals, now I've got 1/2 mv squared. So I plug in my numbers. So v is going to be the square root of 2gh minus the force of friction times the height over m. This is also going to be 2. So this is equal to 7.48 meters per second. Great. Part B. Find the maximum compression of the spring. Keep in mind that the friction force is still acting on this thing. So what does that mean? So let's set this up now. I'm going to draw another diagram. Here it is. It's on the spring. But now I'm going to set my datum here at whatever the compression is, x. This is the initial moment, and then it's going to compress the spring some distance, x. I'm setting this as my datum so that I can have the distance it goes along the rails, I can have the distance it goes down, so the gravitational potential energy, and the compression of the spring, all the same thing, all the same variable x. So for B, I'm going to use this now. I'm talking about this thing. It has gravitational potential energy, mgx. It also has kinetic energy, 1/2 mv squared, and this is this velocity. We are losing energy due to friction, so this is going to be minus the force of friction times x, because that's the distance it goes. The same distance it falls is the same distance it goes, and that's the same amount of compression there is in the spring. At the end, it's reaching our datum that we set. It's coming to a stop, so there's no kinetic energy. And so now I need to solve for x. And so as nasty as this is, we're going to end up having to do another quadratic equation. So this is going to be negative 1/2 kx x squared. And I've got this and this, so I'm going to have plus mg minus the force of friction times x plus 1/2 mv squared, all equal to 0. Okay, questions about that? Write them down. And so now when we plug in our numbers here, again, I don't want to go through it now to waste time in the video, but we plug in the numbers and use the quadratic equation, we should get that x equals 0.915 meters. Okay. So now C, find the distance the cab will bounce back up the shaft. So this fell, and it's going to bounce back up. Well, why won't it go to the original height? Right? It's not going to go to the original height because we've got this friction force. So this friction force is taking energy out, but so that's why it won't go back to the original height. We have to do a new calculation. But we do have to take into account the friction force even on the way up. It's still, this friction force is still acting on it as it goes up. So let me do a new drawing here so we can figure out what's going on here. I already know the compression of the spring, so that's good. So this is it compressed. I'm going to use this as my datum, 0, because whatever height it then gets to at some later time, so this distance here is h. This is where it is at some later time. I'm going to measure the distance from there. So what does our equation look like here? At this point, it has no kinetic energy. It has no gravitational potential energy because it's at 0. All it has is elastic potential energy, and it's the same as what it had over here. So this is 1/2 kx squared. Now we're going to be losing energy due to the friction, and the friction is going to be exerted on this thing the whole height as the spring is extending and as it's going up into the air above the spring. But that's that whole distance h equals mgh. at the end. That's all we got to do. So then we plug in our numbers. X we already know from here. Right? Or you could use this if you happen to have solved for this, but you didn't because we did this. But you could plug that in. But I'm solving for H. So you know the algebra. And the answer that we get is 2.8 meters. Let's take a look then. It says find the approximate total distance the cab will move before coming to rest. Okay. This one we need to be careful the way that we set it up. So here's the cab at some earlier time, or no, rather at the initial moment. Right? It's this some distance above here, and we already know that that's 3.7 meters, right? And then at the end, it's going to be compressed some distance x. So this is x in here, and this is whatever that initial height was. I want to set this as my datum so that my final condition is just 1/2 kx squared. I don't want to have any other energies there, like potential energy, kinetic energy. And kinetic energy won't be there anyway because it's going to come to rest. That means that this height that I actually have to put in above my datum point is h plus x. So I've got mg h plus x. This is the potential energy it has at the beginning. Notice we're setting this up different from in part A. Why? Because I've set a different datum. I'm not going to the datum I had before. It's not coming to a rest and then springing it back upwards. This is just coming to rest on here. And so it's a different amount of compression from in part B. And I don't know what that is. So I've got this, and then I want to know the total distance that it goes. So minus the force of friction times d that total distance, whatever it is. Okay. So I know this height. That was 3.7 meters. But what about x? How do I figure this out? How do I figure out how much compression there is? Well, it's just resting on there. That means if I make a free body diagram of this, I've got the force of the spring that way and the force of gravity this way. The force of the spring is equal to the force of gravity. That means that mg is equal to kx. So I can use this, mg over k, to find what x is. And then I plug this in here and here. I know the friction force. This is the work done, right? The reason I'm putting this in here, by the way, this is the work done that entire time. The total distance, it goes down and up and down and up again. This force of friction is being exerted on it the entire time. And the whole time, it's negative because it's always taking energy out of the system. Right? Realize this negative is not a direction, it's not a vector, it's saying that we're losing energy. It's a subtraction from the total amount of energy. So I know h, I know x now from this. I can plug that in, mg, k, f, all that stuff. Plug the numbers in, do the algebra, the arithmetic, and you should end up with 15.4 meters. Okay. And that is how you use GAPC.